factor of 2 level precision, which really puts you on solid footing to compare with the solar system. Another big part of this program is to observe a thermal phase curve of a hot Jupiter. And so I'm co-leading this part of the program. And we're doing it in the infrared with the MIRI instrument. And the idea here is that the night side of these planets are really cold. And so if you want to have good signal to noise, you have to move into the infrared. And so we're hoping to be able to determine what the clouds are made out of based on how they change the temperature structure of the night side. And we also, another really big goal of this program is to use every instrument on JWST so we can figure out how to use the telescope as quickly as possible during its finite lifetime. I'm also really excited about what we can use JWST for terrestrial planets. So I showed you one result from Spitzer where we're seeing thermal emission from a hot rocky planet. JWST will allow us to do that type of measurement for dozens of planets. And so you can do a survey of what is the occurrence rate of atmospheres on hot rocky planets. I'm writing that proposal right now. And for those planets that do have atmospheres, for the best cases, JWST will be capable of determining in very broad brush terms their atmospheric composition. So here's a simulated JWST spectrum for TRAPPIST-1b for 3 different atmosphere models. Since we don't know what the atmosphere is, we used the solar system for inspiration and took the chemical constituents of an Earth-like, Titan-like, Venus-like atmosphere and then put them at the temperature and pressure, surface gravity expected for TRAPPIST-1b. And you can see that this is for some reasonable number of transits, fewer than 10. Not only can you detect spectral features, but you can also start to distinguish between what molecules are responsible for the absorption. I also want to talk about what can be done from the ground. So here is, the idea here is that it's observing exoplanet atmospheres from the ground is hard because our own atmosphere is in the way. But you can get around this by going to very high spectral resolution, where the spectrum of the planet is actually Doppler shifted as it moves through its orbit. And you can use that fact to differentiate between spectral features from our own atmosphere compared to the planet. And so this is, this is an animation from Henriette Schwartz, where she shows how you can cross-correlate a template spectrum with real data and pick out the radial velocity of the planet. And you can use that to uniquely identify which features are from the planet. And this is super awesome. This is going to be, I think, the most exciting. I'm going to get in trouble if I say it. I am personally very excited about using the ELT class telescopes for this. Harvard, as you all know, is a founding partner in GMT. And you've heard a lot probably from Dave and others about observing molecular oxygen in terrestrial exoplanets using this technique. That is not the only thing you can do. So I am particularly interested in using this technique to search for species that have lower abundance. By going into the core of the line, you can see things that have much lower partial pressures. So one thing you can look for example, is sodium or potassium. For hot rocky planets, the surface is, if it's hot enough, is expected to have a thin vapor atmosphere of vaporized rock. You can look for things like sodium in there, and if you see it, that means that there must be some source of sodium. So if you bake your hot rock for long enough, all the sodium will come out of it. And so if you detect it, that means that there's some kind of turnover. Either there's volcanism or there's tectonic activity that is producing sodium. So there's all kinds of stuff that you can do beyond just oxygen with a spectrograph, like GCLEF, for example. You can also use this technique to measure things like wind speed. So if you observe a hot Jupiter at high enough signal to noise, eclipses the host star, you can get different segments of the atmosphere passing over the stellar disk in turn. And based on the Doppler shift of the planets, of the spectrum, at each successive point you can actually make a map of the wind pattern in the atmosphere of the planet. So really, really cool stuff. Okay. A little farther down the road, Ariel was recently selected by ESA. NASA is contributing a spectrograph to the project. The goal of this mission is to observe spectra for 500 to 1,000 exoplanets, focused mainly on planets larger than 2 Earth radii. And the goal is to really make good on the statistical promise of exoplanets, because we won't have as detailed of information for any exoplanet as we will have for planets in the solar system, but what we do have is a huge sample. So I'm co-lead of the phase curve working group. One of the really nice things about Ariel is that because it's a dedicated facility, there's more time for exoplanets. And phase curve observations are tough because you have to wait for the planet to go all the way around. So this, I think, will be a wonderful complement to the detailed case studies that we plan to do with JWST. Okay, so everything that I have talked about so far has been planets on fairly short period orbits. So I've drawn this red line here. This is about 0.2, 0.3 astronomical units. Those are the transiting planets that we will be best able to characterize in the next 10 years. Longer period planets are tough for multiple reasons. One is that the probability of a transit is lower, so there just aren't that many around nearby bright stars. And the transits don't happen very often, so you have to wait a really long time to catch one. And so this leaves a whole part of this parameter space that will not be explored, including all of the solar system planets. And so in the long term, what can we do to study all of these other planets that are on longer orbital periods? And the answer is to do direct imaging, where you block out the light from the host star with a coronagraph and observe the planet directly. There are 2 approaches to doing this. So you can do it from space, you can do it from the ground. And there are 2 direct imaging focused missions that are currently under review by the 2020 decadal. Here is a simulated reflected light spectrum of an Earth analog from LUVOIR. And you can see this is amazing. You can see spectral features from not only from common molecules like water and CO2, but also from oxygen and ozone, which are canonical biosignatures. You can also do direct imaging from the ground. And there is currently planned a GMT instrument that will be doing this in the infrared. I think that there's a lot of room to develop second light instrumentation to do this in the optical, where you can get reflected light. And so over the long run, these are two things that I'll push very hard for, because I think that as exciting as the transiting planet science is for the shorter period things, we want to see the full diversity of planetary systems. We really want to explore the Earth analogs. And so over the course of my career, this is science that I intend to focus on. Okay, I want to leave plenty of time for questions, so I think I'll wrap up there. Thank you all for coming. Thank you for your attention. And I'll take questions.
Thank you, Laura, for a wonderful talk. I should also mention that there is a Gazette article about Laura's research, and if you that might be interested in other details about her work, you can find it there. Questions?
I actually have almost a demographic question of sorts. None of your targets were Kepler objects,
Oh, yeah.
right? I mean, a lot of them are ground-based, HAT, WASP, and one test object. Just wondering if you could comment on that.
Yeah, definitely. Yeah, so Kepler, so because Kepler had a fixed field of view in the sky, most of the stars were faint. And so to do this type of atmospheric characterization work, I always say every photon is precious. And so really most of the targets have H-band magnitudes brighter than 9. So these are really bright, really nearby stars. And that's why TESS is so important, is because it's scanning the whole sky to find these really bright candidates. Yeah, great question.
Since Charles asked the question at the risk of making Charles unhappy, let me ask.
Don't take it.
Can you imagine using GCLEF on a telescope other than GMT?
Yes, that's a great question. Yeah, so I think this high resolution stuff is really promising. It has not been as vetted as the more traditional low resolution transit spectroscopy. And so I think that already we're seeing some of the ways in which it can be complicated. For example, the stars are really annoying, and they're inhomogeneous. They're, for the purposes of this talk and my research, stars are really annoying. So yeah, stars are rotating, and so their flux is Doppler shifted from one hemisphere to the other. That shows up in this type of high resolution data. There are star spots that are different temperatures, so the spectrum that is illuminating the planet changes. And so I think we're in for a lot of surprises like this before we can really use this technique to push down to the absolute hardest systems and detect oxygen.
So it's good to practice
Good to practice.
existing.
Yeah, so not only good to practice, but also the science is really interesting. You can still do all kinds of stuff without a 30-meter class telescope. A lot of the work that's been done with this so far has been with 4 meters.
Alisa.
You showed us all these wonderful